Came from Politecnico in Bari, and I'm going to present this work about the evaluation of the heat dissipated around the crack tip by means of thermodynamic techniques on two different steel, AISI 422, this is a mastensitic steel, and CF3M, that is austenity one. Okay, we all know that the fatigue crack growth depends on many factors, such as the micro mechanisms that act at the crack tip. In particular, the crack growth can be represented as a function of the stress intensity factor in the Paris law. In the last year, many researchers focused their attention on energy-based approach, because the dissipated energy at crack tip plays a key role in the crack growth behavior. So the aim of this work is to propose a new procedure based on thermographic parameter, the phase signal, that can be correlated with the energy dissipated at the crack tip. I will show the first results obtained on two specimens, one of austenitic steel and one of martensitic one. A first model based on energetic approach was proposed by Wirtman. This model, the crack growth, is related to the surface energy creation. This energy is related to the area of a hysteresis loop. Then Klimbale revised this approach, considering the total plastic energy dissipated per cycle in place of surface energy creation. Then experimentally, Mazzari et al. Found this relation between the crack growth and the energy dissipated per cycle. They measured the energy dissipated by means of experimental measurement of the hysteresis loop. And then they found a similar Paris law model between the crack growth and the energy dissipated per cycle, and the energy dissipated per cycle, and the stress intensity factor. So the question is how can we measure or estimate the dissipated energy, and then how can we measure the area of hysteresis loop? Because this is the method used in the literature, but it's not simple to measure the area of hysteresis loop. Literature, there are different approaches, experimental approach, based on strain gauge, or DIC, or thermography. These latter are very interesting techniques because they provide fulfilled information about the plastic area with the relative simple setup. Generally, the thermographic approach based on energetic one are based on the first principle of thermodynamics, in which the total mechanical energy can be seen as the sum of the heat exchanged by convection, radiation, and conduction, and the variation of internal energy that can be decomposed into two terms: the internal energy used to change the material morphology, and the energy that is dissipated as heat. So, under the main hypothesis that the energy dissipated is totally dissipated as heat, we can measure the heat source with thermography and estimate the energy dissipated at the crack tip. In In this work, we propose the fake signal. Why? This is a typical fake signal profile along the crack growth direction. You can see a double reversal change in sign of phase. Why the phase change? Change because there is a plastic behavior at the crack tip. Moreover, there are high stress gradient that leading to the heat conduction and the loss to adiabatic condition. Then these typical profiles, as we use in literature from Professor Patterson, Thompson, for monitoring the fatigue crack growth. From the face, I can locate the crack tip. And also for measuring the plastic area. Okay, we can consider the plastic area at the crack tip that is characterized by an hysteresis slope. Hysteresis slope means a mechanical phase shift between stress and strain. So this phase, mechanical phase, I call it this mechanical phase, is then strictly related to the area of hysteresis slope. So our idea is, okay, we can use thermographic phase signal that is related to this phase mechanical signal to estimate the energy dissipated at crack tip. And then to study the fatigue crack behavior of material. Okay, proposed approach. We use this temperature model to processing data. We focus our attention on the value of phase, but we take into account other components. For example, the mean temperature increasing, the amplitude of thermal signal at the frequency of the loading frequency, the amplitude of thermal signal at twice of the loading frequency, and the relative phase. This is a typical setup used for test. So this is our procedure. We consider a thermographic sequence. Then we obtain the phase signal information pixel by pixel by processing the data I just showed. Then we consider an analysis area extracted from the total area that consider the plastic area of materials. Then shifting is necessary because the phase is a relative value. So with this step, we report the phase to the zero value in order to measure the variation with respect to the zero reference. So in this case, we consider an area away from the crack tip in which, and the mean value of the phase, and then subtract this value from the value of the analyzed area. Then in this area, we evaluate the minimum value of the phase. These are specimens used for the test. One specimen for each materials. This is the loading frequency, 13 Hertz, the stress ratio, 0.1. And as you can see, the specimen, we use the black paint to uniform and increase the emissivity. These are the amplitude load to have a constant amplitude regular propagation of the crack. This is a setup. We use the loading machine with the capacity of 100 kilonewton. A coolant detector is sensitivity about 18 millikelvin and a frame rate of 155 Hz. The sequences were acquired by RIR software, processing with IRT software. Procedure, as just said, has been carried out following the standard AISI E647. We have each acquisition, acquired a thermal sequence each 2000 cycles, and a pixel dimension of 0.067 millimeter was obtained. Yes, these are the results. Okay, martensitic steel, austenitic one. You can see the different fatigue growth behavior from the two materials. We have a regular propagation of the crack, follow a direction orthogonal to the loading. In this case, we have a change in crack growth direction because we have a different microstructures. Okay, in this graph, the phase value are reported as function of stress intensity factor. Okay, and as you can see, there is a linear correlation in double log scale between the phase data and the stress intensity factor. And the same correlation is obtained by reporting the crack growth rate as function of the phase data. You can see also, also in this case we have a linear correlation. So we have a similar Paris law model. I'll just say found by Mazzari et al. In this specimen, in this test. And in this case, we have the phase in place of the energy dissipated per cycle. So it's very interesting as the phase is capable to discern the different behavior of the two different materials very well. This has the same data, the Paris law data, the crack growth rate, with respect to the stress intensity factor. So, phase seem to describe the different crack growth behavior of material very better. Okay. In conclusion, it was proposed the new thermographic procedure for characterizing the thermal behavior of the crack growth in material on two different steels. The main results. A similar Paris law model was obtained between the crack growth rate and the phase signal. A good correlation between the phase signal and the stress intensity factor has been obtained in agreement with numerical and analytical models present in literature. The phase signal seems to discern in a significant way the different crack growth behavior of the steel. Of course, other tests will be carried out in order to verify the possibility of using a fatigue growth model based on phase data. And the proposed method can be used for monitoring crack growth within real and more complex structures subjected to actual loading conditions. Thank you very much.
Thank you.